The universe is inconceivably big, and there are a lot of extremely big things in it. But at the risk of drifting into the pedantic, we should try to understand what exactly a thing is. This is not an idle topic in metaphysics, because there is a real risk of being fooled by apparent objects or things that look real, but aren't actually really there. Constellations are an obvious example. From our perspective, they look like actual structures of some kind, but that's only because their constituent stars are so many thousands or millions of light years away that our eyes, and often less powerful optical telescopes, cannot detect these distances. That is why the sky looks like a surface, or the inside of a bowl. The chances that the stars in the familiar constellations are all actually associated with each other are essentially zero. We see constellations as distinct entities because of the unsolvability of the distances just mentioned, and also because of a human psychological phenomenon called pareidolia, which is what makes us see faces and figures in clouds, or religious figures in woodwork, or even on pieces of burnt toast. One of the things we will talk about here are areas of the universe called voids, which look from our perspective like discrete entities, but are in fact just empty spaces nearly devoid of stars and galaxies. These empty spaces are real, in a sense, but they are not things, but rather areas that are empty of things, and their edges may be quite indistinct in reality, however sharp they may appear at the distances involved. In art, on the other hand, so-called negative space is a valid concept, and artists from sculptors to bonsai masters actually think in terms of what should be eliminated, so that the finished sculpture or bonsai emerges as a consequence of removal of material. In this sense, perhaps cosmic voids should be considered things after all. These voids have no structure and no internal cohesion. Rather, they are the result of gravity carving out space. They are, however, a clue to what may be the actual biggest thing in the universe, and are also interesting because our galaxy and its local group seem to be in the biggest one so far discovered. Voids and structures are in fact two sides of the same coin, and at least in our universe, there can't be one without the other. So let's take a look at some candidates for the biggest thing in the universe. It must be there somewhere. If we look at the night sky, it's obvious that there are apparent spaces between the stars, and these spaces are irregular in distance. But theoretically, on a very large scale, these local irregularities should smooth out, so that the average density of matter is uniform. This is called the cosmological principle, because the initial Big Bang and the subsequent inflation of the universe should have kept the distribution of matter and energy uniform and smoothed out irregularities. However, it did not. Using a wealth of observational data from various observational sources, like electromagnetic wavelengths such as visible, X-ray, gamma, ultraviolet, and infrared wavelengths gathered from telescope satellites, and computer simulations of these data, we can construct a very large-scale view of the universe, almost as if we were outside it looking in. What we find is that at a medium distance, the universe is spongy or foamy, with stretches of dense matter punctuated by gaps or holes that appear to be empty. It's as if one could take a mass of bubbles and squeeze it together. The result would be stretches where the edges of bubbles press together and the spaces within the bubbles themselves. The areas with the bubble edges were pressed together are where, in our universe, nearly all the visible and probably dark matter occurs. The spaces within the bubbles or voids have almost nothing we can see. Just some isolated, mostly dwarf galaxies here and there, and some dust. If we step far enough away, what we see is the emergence of some kind of cosmic web, an irregular foam of matter and emptiness, with those pockets of apparent emptiness being of varying sizes, ranging from very small, astronomically speaking, to truly gigantic. The threads of visible matter that separate voids, and the accompanying dark matter in those threads, are called filaments, and the empty spaces are called voids. The overall pattern, in fact, looks rather like an electron micrograph of brain neurons, or a gigantic messy spiderweb. This web-like, foamy texture appears to be the result of random, minor fluctuations in matter density across the expanding universe. With matter, both baryonic and dark, concentrated in some places, and relatively empty space in other places. The result was gravitational pull towards what became the filamentous structure, causing other adjacent areas to slowly empty out. It should be kept in mind that all distance and size estimates are just that, estimates and subject to revision. The relatively empty areas we just spoke of, voids, vary in size, some billions of light years across, that are deficient in galaxies and perhaps even dust. There is a reason for this, and it is tied with the structures we see in the universe. These voids may be poor in, though not empty of matter, but they appear to be full of dark energy, which is the force that is causing the expansion of the universe. This is what is causing space itself to expand, rather than the things in space. Simultaneously, gravitation is causing ordinary matter to congregate along the filaments, hence voids form. There are innumerable voids, but there are about 88 currently known voids that are large enough to be noteworthy, at least to some people. Some have even been given names, like the local void and the great nothing. And to complicate things, giant voids may be composed of groups of smaller voids. For instance, there is the giant void called the giant void, about 1.5 billion light-years away and approximately 1.3 billion light-years in diameter. There is also something called the great nothing, often known as the Boötes void, about 330 million light-years in diameter. There is the cold spot, about 1.8 billion light-years in diameter, and about 3 billion light-years distant from us. This cold spot was discovered when it turned out during a survey of the cosmic microwave background that this spot was just too cold. Subsequent study of this area by the Pan-STARRS-1 telescope in Hawaii and NASA's Wide Field Survey Explorer found that statistically, this area was short of the expected number of galaxies by about 10,000. Perhaps one of the smallest voids of any note is the SSRS-2 void, only about 92 million light-years across. There are in fact innumerable other voids of varying sizes, and as noted, large voids appear to be conglomerations of smaller voids. Our own galaxy, along with the local group of galaxies, seem to form something called the local sheet, evidently right on the edge of the local void. The local void is sometimes called the KBC void, named for its discoverers, Ryan Keenan, Amy Barger, and Lennox Coey. Whether it actually exists, or is an illusion of perception and instrumentation, is still debated. Estimates of its extent range up to 2 billion light-years in diameter. Structures, like voids, are to some extent subject to interpretation. Like voids, the distances from and sizes of structures are simply rough estimates and subject to change. Structures are the filaments in the web that is believed to lace throughout the universe, and these filaments contain galaxies, gas, and dark matter. There is some evidence that matter flows along these filaments, and what were once thought to be discrete, independent structures are now suspected to in fact be sections of filaments. What have been in the past considered to be separate structures may actually be sections of one giant structure. These structures may be star clusters, quasar clusters, strings of galaxies or galactic clusters, and so on. At cosmic distances and scales, it's very hard to tell, and astronomers and astrophysicists have just begun to grasp the larger structure of the universe as a whole. But it seems that matter, whether baryonic, ordinary matter, or dark matter, is strung together in a web-like lattice that is spread through the entire universe. For instance, the Great Gamma Ray Burst Ring is a group of 9 gamma ray burst sources, perhaps 9.1 billion light-years away and approximately 5.6 billion light-years in diameter. It resides in a filament, but it may also be a semi-independent, partially self-contained and coherent structure. There is also the Sloan Great Wall, about 1.37 billion light-years in length and about 1 billion light-years away. Another goes by a very prosaic name, the huge LQG, or the Huge Large Quasar Group. This is a group of 73 quasars, about 4 billion light-years in size, and about 9 billion light-years from Earth. Statistical analysis indicates that these quasars are in fact gravitationally linked, which would make them a real discrete structure. This may be a statistical artifact, however, but if it is real, it is indeed both huge and large, and so the name fits, even if this may be a failure of imagination. As another example of this seeming lack of imagination, there is a very large telescope, part of the European Southern Observatory, or ESO, in the Atacama Desert of Chile, called the VLT. This just means Very Large Telescope. The fact is, there are many apparent structures that are enormous in size, far too many to discuss here, but all are apparently associated with filaments. The current title holder for the largest structure in the universe is the Hercules Corona Borealis Great Wall. This is, again, an apparent discrete structure of staggering size, about 10 billion light-years in width, about 10 billion light-years distant from us, and is made up of several billion galaxies. It was identified by the sheer volume of gamma-ray bursts from its source in the Hercules Corona Borealis constellations. It's so big, in fact, that according to current astrophysics, it should not exist, at least as a separate entity. If we want to discuss what might be the largest thing in the universe, we ought to first know if what we are talking about is real, and a discrete, unitary, and cohesive thing. This is where the cosmic web comes in. Seeing a slowed down video of an explosion is interesting, because one can see the energy, in terms of heat and light, rapidly begins to form threads and filaments that surround relatively empty spaces. If the video were stopped at a given frame after a sufficient few seconds had elapsed, it might be possible to name some of the spaces or voids, and name some of the shreds of energy or filaments in that frame. This is what we are beginning to see as we study the universe in greater detail. We are seeing a frame from the development of the Big Bang from 13.78 billion years ago to now. This cosmic web had been theorized decades ago to exist, but until very recently, the technology to imagine it did not exist. Now, however, sections of the web are being imaged for the first time using the MUSE instrument, which is part of the VLT in the Atacama Desert. MUSE is the acronym for Multi-Unit Spectroscopic Explorer, which, as the name suggests, is a very advanced spectrometer, which has recently imaged previously unknown dwarf galaxies in filaments of the web, and has also observed and charted stretches of the filaments themselves, using emissions from the gases in the filaments. The universe, then, is not homogeneous in the distribution of matter. Rather, matter is unevenly splattered throughout the universe, but everything seems to be interconnected via these filaments of matter and gas. Why does all this matter arrange itself into these filaments? The best guess, for now, is random chaotic irregularities that were created during the Big Bang, and then the differential gravitational fields that resulted from these irregularities took over. The best way to look at this may perhaps be to walk it backwards, and start from what we know. In this case, we can see the uneven and spotty distribution of observable matter. We know that there are strings, filaments of matter, and that there are voids. There is evidence that these filaments and voids are where normal and dark matter are collected, and we can trace the current porous appearance of the universe to the consequences of the Big Bang. And this means that the universe contains scaffolding of matter and gravity surrounding voids of relative emptiness. Any other big thing in the universe, as far as we know at this moment, is just a section of this web, This includes the Hercules Corona Borealis Great Wall, the Sloan Great Wall, and anything else you might think of. All of these unimaginably gigantic features of the universe are all sections of this cosmic web. They look like separate entities only because our observations haven't yet caught up with our simulations. But they are not separate entities. They are remnants, sections, cinders, bubbles of the Big Bang. This is what we are beginning to see now. There are lots of things in our universe that look inconceivably large, and so it's natural to ask, what is the biggest thing in the universe? One early answer was the universe itself, but it seems hard to see how the universe can both be itself and also contain itself, without being different from itself. There's a self-referential problem there. But that early answer was pretty close, because it gets at what is contained in the universe that we can see. Just to be clear, it's perfectly fine to discuss objects or regions of things as if they were isolatable, because we do that all the time. And in fact, that's actually how everything is discussed, from science to literature to art and people to cultures to, well, just about everything. It's probably just about impossible to avoid doing this and still sound intelligible. It's mainly a matter of context and subject. In the present case, if we ask, what is the biggest thing the universe contains that is not itself? The answer, at least for now, is the cosmic web. It's the biggest thing in the universe that we know of. It seems to be a real thing, continuous and complete, pieces or sections of which have been thought of as the biggest thing at various times, and it has a clear ontological foundation in astrophysics, with the Big Bang. Thanks for joining us here at Access Astronomy. We hope to see you here next week.